Every second, more than 60 billion neutrinos pass through your body without you noticing. They are invisible particles that traverse planets and stars as if they didn't exist. At the same time, space is expanding faster and faster, driven by a force no one understands. Visible matter represents only a tiny fraction of the universe. The rest is made of something we cannot see, measure, or explain. Physicists call it dark energy, but it's really just a name for our ignorance. In this void filled with enigmas, science advances tentatively, discovering that what we understand is only a tiny part of the whole. At this frontier, the visible blurs with the invisible, and each discovery seems to open up new questions. What are the theories that attempt to explain what we still don't understand about the universe? Multiverse theory. Ever since humankind first gazed at the sky, it has wondered if it is alone. What if the universe we inhabit is not the only one? The idea of parallel worlds didn't originate in a modern laboratory. The ancient Greeks already spoke of infinite realities coexisting. Today, modern physics returns to that intuition with an even bolder question. Do we live in one of many universes? Brian Greene asked himself that very question. As a child, he spent hours observing two facing mirrors and saw an endless chain of reflections. Decades later, he would discover that science also points to something similar. Copies of the universe, repeating themselves in different versions, separated by laws or dimensions we don't yet understand. For centuries, universe meant everything that exists: matter, energy, space, and time. But the discoveries of the 20th century changed that idea. Today, the word can refer only to the portion we observe, or to regions so distant we could never reach them, some even governed by different physical laws. From this arises the concept of the multiverse, a collection of possible universes, each with its own history and rules, where what we consider everything could be just a part within a much larger structure. The fascinating thing is that this idea didn't originate in fantasy, but in physics itself. Various branches, relativity, quantum mechanics, cosmology, and string theory, arrive from different paths at a similar conclusion. There could be multiple realities coexisting. One of the first clues appeared in the 1950s, when physicists were trying to decipher the mysteries of quantum mechanics. This framework revolutionized the way we see the microscopic world. Atoms and particles no longer obeyed certainties, but probabilities. An electron can be in two places at once, and we don't know which one it will be until we measure it. But then the question arises, why do we see only one outcome if all are possible? This gave rise to the so-called many worlds interpretation. In it, each outcome occurs, but in a different universe. In one, the electron is here, in another, over there. In each universe, there is an identical observer who believes they are experiencing the only real version. Thus, reality doesn't choose, it multiplies. Every decision, every quantum event, creates a new branch of the cosmos. The idea sounds mind-blowing and continues to divide scientists. Some believe mathematics supports it, others consider it an elegant fantasy. But its influence has already transcended the laboratories. Films and novels, from The Wizard of Oz to Everything Everywhere All at Once, are inspired by this principle, that every choice creates an alternate world. Beyond quantum physics, the multiverse also appears in cosmology. If space is infinite and the laws of nature are the same everywhere, then everything that can happen will happen, and not just once. Somewhere far away in the cosmos, there could be another Earth, identical to this one, with someone reading these same words. Repetitions would be inevitable. Although we could never see them, they would be too far away. Another path to the multiverse arises from inflationary theory. According to this hypothesis, the universe expanded rapidly after the Big Bang. Greene explains that if this inflation never completely stopped, new regions would continue to form constantly, isolated from one another. Each would have its own properties and physical constants. Each bubble would be a distinct universe within an eternal expansion. And there's more. String theory, which seeks to unify all the fundamental forces, proposes that our universe could be just a brain, a sheet floating in a higher dimensional space. many others could exist, coexisting without touching. And when two of these brains collide, they would release such immense energy that it would give rise to a new universe. In this scenario, universes are born, collide, and are reborn endlessly. The string landscape hypothesis adds another layer. If the extra dimensions can take different forms, each configuration would generate a universe with unique laws. Together, they would form a nearly infinite catalogue of realities, each with its own version of physics. So far, none of this has been proven. There is no direct evidence of other universes. But the curious thing is that the equations that describe our own inevitably lead to the possibility of many more. Scientists didn't invent the multiverse on a whim. Mathematics led them there. Green doesn't intend to convince us that other worlds exist. What he seeks is to show how science, by following its own logic, has pushed us to the limits of understanding. What was once myth or fantasy is now a legitimate question. What if our universe isn't unique? Simulation theory. For centuries, human beings have wondered how real reality is. Ancient philosophers imagined that everything we perceive could be an illusion. Plato represented this with the allegory of the cave, where the prisoners saw only shadows and believed that this was the world. Centuries later, the argument was taken up by thinkers who spoke of dreams indistinguishable from waking life, or of brains connected to machines that manufactured sensations. What was once philosophy transformed in the 21st century into a hypothesis with technological foundations. Nick Bostrom, a philosopher from Oxford, gave it a modern form. If an advanced civilization can create conscious simulations, then it is very likely that we are one of them. Bostrom put forward this reasoning in 2003. He summarized it in three possibilities. 1. That intelligent civilizations disappear before achieving the technological capacity necessary to simulate minds. 2. That even if they achieve it, they decide not to. And third, that they do succeed and generate millions of virtual worlds inhabited by beings unaware of their existence. If this last option occurs, the probability of us belonging to the real group would be minimal. In their logic, there would be so many simulated universes that an authentic one would be the exception. The idea doesn't stem from a desire to frighten, but from a mathematical deduction. If advances in artificial intelligence and computing power continue, a point could be reached where a computer recreates entire brains, with memories, emotions, and perceptions indistinguishable from those of a biological being. In that scenario, millions of conscious digital existences could coexist within the same system. Both authors agree that the exponential growth of computing power makes this hypothesis plausible, to the point that the difference between a simulation and perceptible reality could become unrecognizable. Verk calls this threshold the curve toward the simulation point. The concept isn't just technical, it also touches on the idea of consciousness. If what defines the self is the information flowing through the brain, then a digital mind with the same pattern of connections would have equivalent experiences. From that perspective, there is no essential difference between a biological person and a simulated one. What changes is the medium, neurons or circuits. Bostrom suggests that if such a functional copy were ever achieved, the created worlds could contain individuals who, within their own perception, would be as real as we are. Proponents of the theory even point to possible traces of the code in the structure of the cosmos. Some physicists have observed limits on the energy and resolution of space-time that resemble the grid of a screen. Others interpret certain quantum anomalies as rounding errors or calculation discrepancies in a simulation. Although these ideas are still speculative, they show how modern physics is beginning to merge with computer science to describe reality. For Verk, the most useful comparison lies not in science fiction, but in the systems we already use. In online video games, each player inhabits a different environment within the same server. The characters can interact, but each lives in their own version of the world. If the universe functioned the same way, we could coexist in multiple simultaneous timelines without noticing. Quantum mechanics, with its principle of superposition, would fit as a representation of the probabilistic code that decides what we observe. The implications are profound. If everything is programmed, the laws of physics would be the rules of the software that governs the simulation. Black holes, for example, could act as storage nodes where information is condensed. The Big Bang would be the initial sequence of the system, a kind of cosmic boot. Universal constants, the speed of light, the charge of the electron, would be parameters set by the designer. And entropy, that tendency toward disorder, would resemble the progressive degradation of data in a closed system. Theory of white holes. In the universe, there are regions so strange that they defy everything we know about time. Among them, one idea stands out for how impossible it seems: the white hole. The hypothesis didn't arise from observation, but from the mathematics of general relativity. By studying Einstein's equations, physicists discovered that they admitted a symmetric solution, a version where time runs in reverse. In this model, the collapse that forms a black hole could have its opposite, a kind of outward explosion. What in one is confinement and falling, in the other would be release and expansion. Stephen Hawking explained that space and time are intertwined. In an environment of extreme gravity, like that of a black hole, space is curved so much that time changes direction. Inside the event horizon, moving forward is equivalent to falling. If that direction is reversed, the equations describe an inverse phenomenon, a place where everything moves away and nothing can return. That is called a white hole. In the 1960s, John Wheeler and Martin Kruskal proposed a visual image to understand this phenomenon. They imagined two extremes of space joined by an invisible tunnel, the Einstein-Rosen bridge. On one side would be the black hole, where time moves forward. On the other, the white hole, where time flows in the opposite direction. According to their calculations, both could be parts of the same structure, connected by a passage that would allow matter swallowed at one point to appear in another universe. It would be, in theory, an exit through the fabric of space-time. Hawking understood that classical physics was insufficient to describe these limits. From quantum mechanics, he showed that black holes are not completely black. They emit radiation that causes them to lose energy over time until they evaporate. This effect reveals that under extreme conditions, gravity and quantum mechanics intertwine in ways that classical theory cannot explain. The physicist Carlo Rovelli revisited the idea from a more modern perspective. In The Order of Time, he argues that the notions of past and future are not universal. Each system experiences time differently, and under extreme conditions, it can even be reversed. In such environments, the sequence of events loses its usual meaning, and what appears to one observer as disintegration could be formation for another. Rovelli proposes that white holes are not simply mirrors, but regions where the conditions of the universe are reversed. In these regions, entropy, which normally increases, could decrease, causing the arrow of time to point in the opposite direction. In practice, these objects would be extremely unstable. Unlike black holes, they would disintegrate almost immediately, releasing all their energy. Although compatible signals, such as certain gamma-ray bursts, have been sought, so far there is no direct evidence of their existence. Along the same lines, an even more radical idea is introduced. If time is not a constant of the universe, but an emergent property, a white hole could be a manifestation of this reverse emergence. In this view, the cosmos does not have a central clock. Each system defines its own rhythm. Where gravity is extreme, as in a black hole, time seems to stop. In its theoretical counterpart, the white hole, time could begin again in the opposite direction. This interpretation fits with loop quantum gravity, where space and time are made up of discrete units capable of rearranging themselves, creating the appearance of a new beginning. Although one has never been observed, the theory of white holes remains a powerful tool. It allows us to imagine how the universe behaves when the laws of relativity and quantum mechanics meet. At that boundary, time ceases to be a line and becomes a flexible variable. What from one perspective appears to be destruction, from the other could be creation. Perhaps, as Hawking suggested, everything a black hole devours doesn't disappear entirely, but rather awaits the moment, or the place, where the universe decides to return it. Space-time as a superfluid theory. For centuries, space was thought to be merely a void where things floated. Einstein changed that idea by demonstrating that space and time form an elastic structure that deforms with matter and energy. However, some contemporary physicists believe that this structure could have an even deeper nature. It might not be a stage, but a substance. The superfluid spacetime hypothesis stems from a simple question. If everything in the universe has a material basis, why shouldn't space itself? Perhaps the vacuum is a kind of invisible fluid that behaves like a superfluid, a frictionless substance that can flow without losing energy. Carlo Rovelli presents this from a revolutionary perspective. In Reality is Not What It Seems, he explains that the laws of gravity do not describe a static background, but a dynamic fabric composed of events. At the smallest scales, this fabric would fragment into tiny units of space and time, like atoms of reality. Instead of a continuum, the universe would be composed of a quantum network that vibrates and transforms ceaselessly. When this network moves collectively, its behavior resembles that of a superfluid, a medium that curves, stretches, and ripples without resistance, transmitting energy and gravity simultaneously. Rovelli proposes that space and time are not fixed or fundamental, but rather the result of much smaller processes. Just as water only exists when many molecules move together, space-time would be a consequence of the collective behavior of tiny units called quanta of gravity. What we perceive as the curvature of space would not be a property in itself, but the effect of these quanta moving together, like a current that appears continuous, even though it is made up of millions of droplets. From this perspective, the universe is not composed of separate objects, but of connections. Each point in space only has meaning in relation to others. Roger Penrose, for his part, approached it from a more mathematical angle. In The Road to Reality, he develops the idea that space and time arise from deep geometric structures that obey elegant laws. Penrose suspects that the vacuum is not simply nothingness, but a condensation of quantum energy that behaves as a continuous field. In this sense, space-time would be similar to a quantum superfluid, uniform, coherent, and capable of sustaining propagating waves without dissipating. In fact, in theoretical physics, superfluids are known to exhibit properties almost identical to those of space. They allow the passage of waves, respond to perturbations, and can rotate, creating vortices analogous to black holes. In laboratories, superfluids like helium-4 have shown behaviors that seem to echo cosmology. They can climb walls without friction, form stable eddies, and transmit energy without loss. If space-time shares these properties, it would be a medium that can expand, curve, or vibrate without wearing down. The Big Bang, in this context, would not be an explosion in a vacuum, but a phase transition in a cosmic fluid. Rovelli compares this idea to music. Space-time would not be a written score, but a symphony in progress. Each particle would be a note within a universal melody. In this framework, gravity would not be a force, but the result of the collective motion of this fundamental fluid. From a different perspective, but with a similar intuition, other physicists have reached similar conclusions. Penrose approaches the question from a different mathematical perspective. For him, space-time is not a material substance, but a coherent structure capable of transmitting information continuously and without loss. This continuity would help explain why the universe maintains its overall shape and why gravity acts as a smooth but persistent interaction. From this shared perspective, both agree that, at extreme scales, such as inside black holes or in the first moments of the universe, space-time ceases to behave as a continuous fabric and becomes granular. Each quantum fragment would act as a small unit of that fluid, and when combined would give rise to the continuous appearance of space that we perceive, the ekpyrotic cyclic universe. Theory. For much of the 20th century, cosmology accepted a single story. The universe began in a gigantic explosion, the Big Bang, and everything has been expanding ever since. However, some physicists refuse to accept that the cosmos was born from nothing. Among them, Paul Steinhardt and Neil Turok proposed an alternative that challenges the very principle of time. The universe had no beginning and will have no end, but rather renews itself again and again in an infinite sequence of cosmic eras. In Endless Universe, they describe what they call the ekpyrotic model. a word borrowed from ancient Greek meaning creative fire. The central idea is that the current universe is just one stage within an endless cycle of expansion, collapse, and rebirth. Instead of a single Big Bang, there would have been countless bounces, where the cosmos is compressed to extreme densities and then expands again, beginning a new era. Each cycle would be a page in a book without beginning or end, where the universe dies only to begin again. According to Steinhardt and Turok, this process takes place within a space of additional dimensions. Our universe would be one of the membranes, or brains, floating in a space of higher dimensions. When two of these brains collide, the released energy triggers a new beginning, a burst of light and matter that gives rise to a new expansion. This impact would be what we interpret as a Big Bang, but without the initial singularity. The rebound transforms the accumulated energy of the previous cycle into the spark of a new expansion. What we see as a beginning would, in reality, be the continuation of a previous cycle. The authors argue that this model solves several enigmas that the Big Bang cannot explain. For example, the problem of the homogeneity of the cosmos. If the universe was born from an explosion, why are temperature and matter so uniformly distributed? In the cyclic model, this uniformity is not a mystery. It is inherited from the previous phase. Each rebound leaves the universe almost in equilibrium before expanding again, as if the cosmos learns from its own mistakes after each rebirth. Another advantage of the ekpyrotic model is that it avoids the notion of singularity. In the classical Big Bang, density and temperature reach infinite values that the laws of physics cannot describe. In contrast, in a cyclic universe, the contraction stops before reaching that point, and the accumulated energy is transformed into the momentum of the next expansion. The result is a universe that breathes. It contracts, expands, and starts again. Steinhardt and Turok propose that each cycle lasts trillions of years. During the expansion, galaxies move apart, and space cools until it becomes almost empty. After a long period of stillness, the attraction between brains pulls them together again, and the collision initiates a new cycle. At that moment, energy is converted into matter and radiation, repopulating the cosmos. What we consider the beginning of everything would be just a transition between two cosmic ages. Unlike the inflationary model, which introduces a violent expansion in the first moments of the Big Bang, the ekpyrotic model offers a gentler and more orderly explanation. The uniformity of the universe, the distribution of matter, and the small fluctuations that gave rise to galaxies would be natural consequences of the collision process between brains. The energy of the impact would generate waves that propagate through the newly formed space, sowing the irregularities necessary for cosmic structures to emerge. In this scenario, time never began. There is no first moment or initial boundary. Each cycle prepares the conditions for the next, keeping the total amount of energy constant. With each rebound, the universe is renewed, but it retains some of the information from the previous one, as if each version inherited an echo of the past. This continuity avoids the philosophical problem of the first origin and eliminates the need for an absolute starting point. The model also redefines the fate of the cosmos. In the traditional view, the universe can expand eternally or collapse in a final big crunch. In the cyclical scheme, both processes are stages in the same sequence. When expansion is exhausted and dark energy begins to dominate, space stops growing and begins to contract. This contraction does not destroy the universe. It prepares it for its next rebirth. Each cycle is born from the death of the previous one, not from its emptiness, but from its fullness. Everything that collapses is transformed into the spark of a new beginning. Steinhardt and Turok emphasize that the ekpyrotic model does not contradict current observations of the universe. Big Bang Theory. Everything that exists, matter, energy, space, and time, was born in a single instant. This is the premise of the Big Bang Theory, the most widely accepted explanation for the origin of the universe. According to this view, some 13.8 billion years ago, all of reality was concentrated in a tiny, hot, and dense point. From that singularity, an unimaginable expansion marked the beginning of everything we know. Stephen Hawking explained it directly. Before the Big Bang, there was no before. Time itself began with that expansion. There is no previous moment because time itself emerged there. This statement eliminates one of the oldest questions. What existed before the beginning? The answer is that the concept of before was meaningless. The Big Bang was not an explosion within space, but rather the expansion of space itself. There was no center from which everything moved away. Every point in the universe moves away from every other point because the very fabric of space stretches. Guido Tonelli, in Genesis, describes the initial void as something that was never truly empty. In that apparent nothingness, energy fields vibrated, producing ephemeral particles that appeared and disappeared ceaselessly. From this agitation arose the spark that gave birth to the universe. A tiny change in that quantum foam was enough to release the energy that transformed into matter, light, and space. From that instant, the universe began to grow at a dizzying pace, expanding faster than light in its earliest moments. In the first few seconds, the temperature was so high that no structure could exist. Elementary particles floated in an ocean of pure radiation. As the cosmos expanded, it cooled, and with that cooling, the particles were able to combine. Protons and neutrons formed nuclei, and later electrons joined them to give rise to the first atoms. The once opaque universe became transparent, and light began to travel freely. That light is still present today as the cosmic microwave background radiation, the fossilized echo of the birth of time. For centuries, humanity believed that the universe was eternal and immutable. Aristotle imagined a perfect cosmos that had always existed. Even Einstein, when formulating general relativity, thought the universe must be static and went so far as to modify his equations so that it wouldn't expand. But Edwin Hubble's observations in 1929 changed everything. Studying distant galaxies, he discovered that they were all moving away from us, and the farther away they were, the faster they were moving. This was evidence that space was expanding. If everything is moving apart, there must have been a time when everything was together. Hawking explained that this expansion doesn't mean that the Earth occupies the center. It is space itself that is growing in all directions, as if each point were the center of its own universe. In the following decades, the Big Bang model was consolidated thanks to three decisive pieces of evidence: the expansion observed by Hubble, the abundance of light elements such as hydrogen and helium, and the discovery of the cosmic microwave background radiation in 1965. This faint signal, captured by accident by engineers Penzias and Wilson, confirmed that the universe had passed through an extremely hot phase. The radiation that filled the cosmos since then had cooled to just 3 degrees above absolute zero. Tonelli describes this radiation as a photograph of the newborn universe. It reveals tiny temperature irregularities that represent the seeds of galaxies. Without these minute fluctuations, the cosmos would be perfectly uniform, and no stars or planets would exist. What we see in the sky today are the traces of those tiny initial differences, amplified by billions of years of evolution. As the universe expanded, its history became more complex. After the first 3 minutes, matter began to clump together under gravity, forming the first clouds of gas. These concentrations collapsed and ignited the first stars. Heavier elements were forged in their cores, and when these stars died in violent explosions, they scattered these materials into space, setting the stage for new generations of stars and planets. Everything we are, the atoms in our bodies, the iron in our blood, the carbon in life, comes from that stellar cycle that began with the Big Bang. But the model also raises profound questions. If the universe emerged from a singularity, what caused that expansion? Hawking insisted that an external trigger is not necessary. The laws of physics are sufficient to explain its origin. Steady-state theory. In the mid-20th century, while most astronomers accepted that the universe was expanding, a small group of scientists resisted the idea that everything had a beginning. If space was growing, they reasoned, new matter must be appearing to maintain its constant density. Thus was born the steady-state theory, a vision that proposed an eternal cosmos. without beginning or end, where creation was continuous and silent. Simon Singh recounts that this idea was developed by three men: Fred Hoyle, Herman Bondi, and Thomas Gold. They worked in Cambridge in the 1940s, in the immediate aftermath of the war, when science was seeking stability after years of destruction. Their proposal reflected this desire for permanence. Instead of a universe that was born and died, they imagined one that remained always the same, gradually renewing itself as it expanded. The starting point was the same observation that underpinned the Big Bang theory. Galaxies were moving away from each other. But Hoyle and his colleagues offered a different interpretation. For them, this expansion did not mean that the universe had an explosive origin. They maintained that although galaxies were moving apart, new stars were continuously forming in the gaps they left behind. In this way, the cosmos would always retain the same average appearance, without aging or global evolution. The key to their model was the perfect cosmological principle. According to this principle, the universe is homogeneous and uniform not only in space, but also in time. There is no privileged moment or central point. The entire cosmos, they said, looks the same in any direction and at any time. If we observe a group of galaxies today and look at it again a billion years from now, its average distribution would be the same. For this to happen, there had to be a mechanism for the continuous creation of matter, atoms being born spontaneously from the void, one every few million years, and for every cubic kilometer of space. The quantity was so small that it was impossible to detect, but sufficient to keep the total density constant. Fred Hoyle defended the theory with an impressive confidence. It was he who, in a radio interview, used the expression Big Bang disparagingly to refer to the rival theory. Unwittingly, he coined the name by which that other idea would ultimately triumph. For Hoyle, the universe didn't need an initial explosion or an external creator. It was eternal, self-regulating, and always new. Singh explains that this view was attractive because it eliminated the problem of origin. If the universe had always existed, there was no need to ask how it began. Continuous creation filled the gaps left by the Big Bang. During the 1950s and 1960s, the steady-state theory had influential proponents. Its supporters argued that it fit with the available observations. New galaxies detected at great distances seemed to confirm that the cosmos was regenerating itself. However, advances in astronomy began to show evidence that contradicted this idea. Radio telescopes revealed distant objects unlike any galaxies we see today, quasars, radio sources, and young clusters that pointed to a different past. If the universe had always been the same, such differences shouldn't exist. The final blow came in 1965, when Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation. It was the echo of a hot, dense universe in its early stages. No steady-state model could explain this uniform radiation coming from all directions. While Big Bang proponents saw it as proof of their theory, Hoyle tried to reinterpret it as the result of local processes, but his arguments failed to convince. Even so, the steady-state theory didn't disappear immediately. Some scientists valued its elegance and philosophical coherence. In a way, it represented a resistance to change. An eternal, self-sufficient universe was easier to accept than one born from an incomprehensible instant. Singh points out that the dispute wasn't just scientific, but emotional. Proponents of the steady-state theory saw in the Big Bang a return to the ideas of divine creation that science had tried to overcome.
The Goldilocks planet theory. For centuries, humankind observed the sky, wondering if other worlds like their own existed somewhere. With the advent of modern science, this intuition became a concrete quest to find planets where life could arise. Astronomers call this band of the cosmos, neither too cold nor too hot, the Goldilocks zone, a reference to the fairy tale where everything had to be just right. Carl Sagan explained that life is a natural consequence of the universe's chemistry, but also an extremely fragile phenomenon. For it to appear, a planet must meet specific conditions: a moderate temperature, a protective atmosphere, a stable star, and just the right distance for water to remain liquid without boiling or freezing. This thin band around a star is what defines habitability. Earth is located right in the center of the sun's Goldilocks zone, and this cosmic coincidence has allowed oceans to exist for billions of years. cosmos, Sagan describes Earth as a blue droplet suspended in darkness, a geological and biological miracle sustained by equilibrium. If it orbited a little closer to the sun, the water would evaporate, and the planet would resemble Venus, shrouded in toxic clouds and unbearable temperatures. If it were a little farther away, the water would freeze, and the surface would be trapped under eternal ice, like Mars. The lesson was simple. Between these two extremes, there is only a narrow margin where life can flourish. With space exploration, scientists began to compare these limits. The probes that visited Mars and Venus in the 1970s confirmed that these worlds, while similar to Earth in size or composition, were completely inhospitable. Sagan participated in these missions and became convinced that habitability depended on more subtle factors than distance from the sun. Atmospheric pressure, the presence of greenhouse gases, the magnetic field, and geological activity determine whether a planet can maintain liquid water and a stable climate. In his view, life is a matter of thermodynamic equilibrium, not a miracle. Decades later, David Grinspoon revisited this idea from a broader perspective. In Lonely Planets, he suggests that Earth might not be the exception, but rather one of many possible combinations of chemistry and climate that allow for life. He defines the habitable zone as a dynamic, not fixed, concept. As stars age, their brightness changes and the Goldilocks zone shifts. A world that is temperate today could become hellish within a few million years. In this sense, life not only needs a suitable environment, but also enough time to adapt before conditions change. Grinspoon points out that habitability shouldn't be measured solely in terms of water. There are moons with subsurface oceans, such as Europa and Enceladus, where energy comes from internal heat rather than sunlight. These environments, though icy on the outside, could harbor ecosystems similar to those that thrive deep within Earth. The Goldilocks zone, therefore, is not a rigid line, but an idea that evolves with each discovery. The development of more sensitive telescopes allowed the detection of the first exoplanets. Many of them orbit stars other than the sun, some so close that their years last only days. From these observations, astronomers began to classify worlds according to their position relative to their star. Some were too hot, others too cold, and a few seemed to be just in the right range. Sagan had imagined this scenario decades earlier, convinced that the universe must be full of places where life could try to take root. However, both Sagan and Grinspoon cautioned that the right distance does not guarantee life. Climate stability, chemical composition, and protection from radiation are equally essential. On Mars, for example, the average temperature could allow for liquid water, but its atmosphere is too thin to retain it. On Venus, the opposite is true. The pressure and carbon dioxide have transformed the planet into a permanent oven. Both cases serve as a reminder that balance is the exception, not the rule. Theory of sterile neutrinos. For decades, physicists have searched for the pieces that complete the invisible puzzle of the universe. One of the most elusive is the neutrino. Leon Letterman described it as the ghost of physics, a traveler that passes through matter without leaving a trace. Every second, trillions of them cross the Earth, our bodies, and walls without anything stopping them. They are so abundant that they outnumber the atoms of all the stars in the cosmos, and yet they hardly interact with anything. This paradox has made neutrinos one of the greatest mysteries of modern science. Their existence was proposed in 1930 by Wolfgang Pauli, when he noticed that energy was missing in radioactive decay experiments. To overcome the laws of conservation, he imagined a neutral, tiny, and undetectable particle. No one had seen it, but the equations required it. Later, Enrico Fermi developed a complete theory about this particle, which he called the neutrino, little neutral, in Italian. From that moment on, the experimental hunt began. More than 20 years would pass before the first real proof was obtained. In the 1950s, Clyde Cowan and Frederick Reines installed a detector near a nuclear reactor and captured a faint signal, a flash that confirmed the existence of the neutrino. It was the first time the invisible had been seen. This opened a new field in physics, and half a century later, Reines would receive the Nobel Prize for this achievement. Letterman explained that, although neutrinos seemed insignificant, their role in the cosmos was fundamental. In the heart of the sun, every second, millions of tons of hydrogen fuse into helium, releasing energy and neutrinos. These escape instantly and travel at the speed of light, one but three types, electron, muon, and tau, and as they cross space, they would alternate between these forms. This phenomenon, known as neutrino oscillation, implied that they had mass, albeit minuscule, an unexpected blow to the standard model of physics. Frank Close, in his book Neutrino, explains that this oscillation revealed new physics and opened the door to an even stranger possibility, the existence of a fourth type, the sterile neutrino. Unlike the other three, this one wouldn't interact even through the weak force, making it virtually undetectable. Only their gravitational effect, or their influence on other neutrinos, could betray their presence. The idea of sterile neutrinos arose to explain observations that didn't fit with known theories. Some experiments in nuclear reactors detected more or fewer neutrinos than expected. Others, in space, showed signals suggesting the presence of an additional type. If they existed, they could be part of dark matter, that invisible substance that makes up most of the universe and holds galaxies together. Liederman saw this as a cosmic irony. Particles impossible to see could be the ones that sustain the structure of the cosmos. Sterile neutrinos would represent a bridge between visible and invisible matter. If their mass were sufficient, they could explain why galaxies don't disperse and why the universe behaves as it does. But if their mass were almost zero, they could act as an echo of the Big Bang, fossilized remnants of the first seconds of existence. In both cases, their role would be essential to understanding cosmic equilibrium. Attempts to detect them have multiplied. Underground laboratories, such as those in Italy, Japan, and the United States, are building giant detectors of transparent liquid capable of registering a single flash among billions of particles. However, sterile neutrinos do not emit direct signals. Their shadow is sought in the data, their trace in the tiny deviations of the statistics. It's like trying to find a missing node in